All right, thanks everybody for joining today. The talk that we have lined up is from former boss and good friend Eric Lloyd at the University of Michigan. And he's going to be talking about the NetBASILISK project, which is a security architecture that they're implementing on the campus of the University of Michigan. So I will turn it over to you, Eric.
Thanks, Jason. Can you hear me all right?
Loud and clear.
All right, great. Delighted to have the opportunity. When Jason and I first talked about it, I dreamed of giving this from my basement. So here I am. Hope you're all doing pretty well and that everybody's staying healthy. A little bit about NetBASILISK. It's an acronym, obviously. It does mean something. It means border at scale, integrating and leveraging individual security components. And I have to keep looking that up. But it does talk about how we are trying to approach network security at the University of Michigan. It also is a project of how we support data-intensive science. So I'm really trying to hit those two themes here today. So a little bit about where I work. I'm the director of networks, which means I'm responsible for the campus network, everything from the Wi-Fi up to the internet connection, except for the network for Michigan Medicine. And I'm also responsible for the campus data centers as well. All right. Sorry. I'm not getting a slide to advance. There we go. All right, so a little bit of context. We have a new CIO, Ravi Pense, who came to us from Brown University. And he laid out as the future vision for the networks at the University of Michigan is that our goal is to build a world-class network that is available in every campus location at any time for our students, faculty, and staff in a manner that outpaces data-intensive research needs of our most talented scientists. And that's a tall order, but one we try very hard to meet. And a lot of that is about building a big enough network that we don't slow down the science, but it's also about making sure that we deliver security in a context that also allows the science to proceed as unhindered as we can. And that sort of context was sort of the route for where we got to. So a little bit about some of my co-PIs. I'm privileged to be able to work with Alex Halderman at the College of Engineering in the EECS department, Michael Cianfrocco at the Life Sciences Institute. He's a structural biologist, and Sean McKee, who many of you may know, who works for high energy physics at the University of Michigan as well. Also, in addition to my team within the ITS infrastructure networking arena, we work closely with information assurance under Saul Berman, who's the CISO for the university. Just a little bit about how we're divided up. The CISO is responsible ultimately for security at the university. However, my team tries to work within what they sort of lay out, and we're responsible for operating many of the network security devices on campus in addition to running the networking. So let me talk a little bit about our strategy. So the context here is that obviously network security, there are trade-offs between availability, security, and performance. And we have some pretty non-negotiable security standards around keeping devices secured, keeping users, making sure that users are authenticated and following our standard practice guide, that's what SPG stands for, at all times. And our components are everything from access control to analytics to firewalls to IPSs, network segmentation, security information and event management, VPN, wireless security. So we have a lot of different tools in our toolbox, but we didn't necessarily, when we started, have all the tools that we needed. And then obviously we want to ensure the security of our network as well. So let me jump into the meat of it. So I'm going to put up some really simple network diagrams here just to sort of give the context of what problem we were trying to solve and specifically how the university might differ from some other universities. When I'm telling a really simplistic story, I say the typical university built a network and said, this is great, and then said, wait a minute, the internet's dangerous, and they put up a border firewall. And then they said, wait a minute, we broke science, and they follow some of the science DMZ practices laid out on the faster data site, and maybe add in some DTNs and some of the later innovations you've seen as well. The University of Michigan didn't necessarily follow all that path, which is partially why we're doing some things in a little bit different way. But fundamentally, as it currently stands, we have a 4-node network core that's a 100 gig ring. And each academic unit kind of hangs off that network core. There's 2 nodes on central campus and 2 nodes on north campus. And most buildings either hang off the 2 central campus nodes or the 2 north campus nodes. And my boss likes to say that the University of Michigan is 19 schools and colleges with a common football team. And so there's a long tradition of independence. I think the College of Engineering's networks were only integrated with ours, with the central IT networks in 2013. And we are just now starting to work with some of our sister campuses at Dearborn to integrate them as well. And so, and then Michigan Medicine is the last unit that still wholly runs its own network, but the units are still responsible for their networks. And so what that means from a security perspective is that the individual unit buildings connect to our central core, then we go out through 2 border routers out to the internet. And from a security posture, initially all the units were running their own firewalls, and our campus core was just on the internet. There was no border firewall, and there never actually has been. And so over time, first we had a virtual firewall, now we have a next generation firewall. Over time, we were able to sort of start centralizing that decentralized unit firewall. So essentially, some of the units are still running their own firewalls. Some of them are buying individual firewalls and letting us run them for them. And then some of them are basically outsourcing that unit firewall task to us through our centrally managed next generation firewall. And I mention this because we kind of take a defense in depth approach. And we also have a second layer of defense. And so a few years before I got here, we put in place some intrusion protection systems as well between the campus core and the border. And what I would note here is if you look at the bandwidths, the handy bandwidths, we basically have 20 gigs through the campus core, but we have 100 gig links out to the internet. So right there, it's very clear that we can't run all connectivity through the IPSs. It just simply won't hold up. Our prototypical example of a sample scientific researcher was a member of the genomics team who decided to move 23 petabytes to Google Cloud because he got a better rate on some of the compute there, and just started doing it. And as we did have to ask him to give us a little bit to give us a weekend to reconfigure the network to make it possible for him. But our goal going forward is really not to block that kind of science, that people ought to be able to do that. And so the question is sort of how do we create something between our border routers and the internet while still enabling that science? And I should point out Michigan Medicine is here as well. They're connected into our border too, but they also run their own firewalls. And the reason I call them out is they're about half or a little more than half of the research at the university, which is just shy of 2 billion, if I remember correctly. So what I'm going to talk about today when I'm talking about NetBASILISK, we also call the network border intrusions or inspection system, NBIS. And so we're going to talk about trying to create a layer between our border routers and the internet there. I'm just going to check, and Jason, can you still hear me okay and everything going all right?
Yep, looks good. Here, sounds good.
Okay. So what we would eventually like to do is to get rid of those IPSs and just have the border security solution that we're talking about here today. So that's a little bit of context of what we're trying to accomplish. So we didn't do this in a vacuum. We started when I joined the University of Michigan, a network security strategy review. And we worked with some of the key units like our HPC unit, like Dearborn, like Michigan Medicine, and our larger campus units to kind of come up with a network security strategy, figure out what our requirements were and what we were trying to accomplish. And we also have a University of Michigan Network Governance Group, which is composed of the IT leads for the various units that effectively acts as a board of directors, for lack of a better term, for our running of the network. So it's a way where we can present sort of what we're doing in terms of growing the network to the units to get their feedback to make sure we're doing this in a way that's consistent with them. And so we ended up getting a proof of concept done sort of September of 18 to February of 19. Shortly after, we put in a solicitation for a CC Star Integration Award, which was awarded towards the end of last summer. And we've sort of been ramping it up ever since, trying to get it built out. And sort of this is sort of not quite 1 year, it's a more like 6 to 9 month check-in point. But I think we've made a fair amount of progress so far. And so that's kind of what we're talking about today. So let's talk a little bit about that proof of concept. When we did our strategy discussion, and we're certainly not the only university to have done this, we gravitated towards what was then known as BRO and now known as Zeek, and put in place a proof of concept. But we did have some ideas of doing it a little bit differently, and I'll talk about those as well. So, you know, the question is sort of a scaling thing. And the way I kind of think about it, again, this is probably a little bit oversimplistic, is if you can afford a 10 gig router, you can probably afford a 1 gig security device. And if you can afford a 100 gig router, maybe a 10 gig security device. That's a little bit oversimplistic, but it seems to be about the math that even though we can easily afford 100 gig routers, you can't really afford the comparable security devices. You know, so I mentioned earlier that we can't run all of our campus traffic through the border IPS. It protects about 27% of the networks on campus currently. And that inspection throughput capacity is about 20 gigabits per second. And our wireless networks alone can exceed that when classes are in session. And the cost of scaling that up to 300 gigabits per second was prohibitive. We actually did an RFP. We had a vendor who said they could do it, and then they won it, and then once we got into the details, they're like, oh, wait a minute, that would cost twice as much. Oh, wait a minute, that would cost 10 times as much. Oh, wait a minute, we can't actually do that. So, you know, if we could have bought an off-the-shelf solution here, I think we probably would have, but we just couldn't find a vendor that would do that. Likewise, for our NGFW, it has as I said earlier, it has a different goal. It's a continuation of the opt-in firewall solution for campus. It's not meant for research workloads at scale. And so that really wasn't what we needed either. I mentioned that we did a proof of concept. It had a lot of function, but it just couldn't scale to what we wanted, provide the inline mitigation, or support the tapping and net flow needs, or the east-west flows that we wanted to look at as well. So the basic proof of concept goal was to examine a custom network border security system and make sure it scaled to the university's network capacity needs. And that took us 4 or 5 months. And it appeared to basically be able to scale to the level that we wanted and keep up with the amount of data that we wanted to inspect. So I'm going to go through a little bit where we're at today. But I'll mention that, you know, none of this should be a surprise for folks who are familiar with BRO. You know, we had a Zeek cluster, we had the Arista hardware to do tap aggregation. The things that were different is we looked at including the Corsa NSC 7200s in it, and that's the route we eventually went, and I'll talk about the pros and cons of that. And we also looked at the CoreLight sensors, and for those who aren't aware of CoreLight, it's the company that was stood up with most of the Zeek developers in it, if not all. They still support the open source Zeek, but they're also building a commercial product. And for the university, at least, there are always some advantages with going with a commercial product in terms of support, but we also looked at the open source approach as well. And then the last thing we looked at was trying to find an affordable logging solution. I think logging is actually a huge component of building this type of system. And we've probably spent as much time thinking about the logging as we have about the system itself. How do you build it in an affordable way? If we have 400 gig of connectivity to the internet today and we expect to scale to 1600, How can we afford the logging that will go along with that system? So that was completed. We successfully implemented all our components. We got assurances for the support and partnership from the vendors, and we got a really good understanding of the components and how they kind of played along. And from there, we kind of segued immediately into the NBIS project. And I'm using two words here. I'm using NBIS and I'm using NetBASILISK. And so they're essentially the same thing in the sense of they are the common hardware. But NBIS is the project to essentially build a production system for the university, while NetBASILISK is the research endeavor to make sure that we are not breaking science in so doing it. And so that's sort of the distinction. I'm talking about both of them, but NBIS is more the production side and NetBASILISK is more the research side. So I'm going to take a little segue here and talk a little bit about some of our networks and sort of explain in context how this fits and what we did. This was the network that was in place more or less when I got here. This has some enhancements to it, but essentially over on the left where you see RFXB, RLSA, RSCB, and RCool, those are our 4 cores from the previous picture. And then there's the 2 border routers as well with Michigan Medicine hanging off of them. You can see the bypasses that go through the IPS that are 2 by 10 gig each. And you can see at the time, we kind of had this, well, at this point, we've gotten it up to 400 gig links. For a while, it was only 3 with an additional border router and using Mylar, which is a joint project with Wayne State and Michigan State. And now with Merit kind of running it for us to provide additional connectivity to Chicago. And so it was a fairly complicated endeavor. And the question was sort of how do we put in place the border security solution that we want? So after some changes, this is what the solution looks like today. It's a little bit deceptive in that it shows 5 NBIS nodes when there's really only 4, and one of them is also going to Comcast. But for the most part, this is an accurate representation. We have 400 gig links out. 2 of them ride over Merit, 2 of them ride over Mylar, which Merit administers. And those 2 essentially go to the BTA OmniPoP, and then from there to Internet 2 as well. And so in this environment, we basically have put a border in place between campus and the Internet as a whole across the board. I'm going to skip some of the details here. Well, let me actually do this 5th one. The other thing that's going on here is separately outside the scope of this project, we are also rebuilding our campus core, collapsing it from 4 physical nodes down to 2 physical nodes, although it may end up being 4 virtual nodes within that, and essentially rebuilding the fiber plant on campus as well to enable us to support at an affordable price 2 by 100 gig into every building on campus, about 250 buildings in total. So that's coming too. And so while that's outside the scope of this project, that's the kind of bandwidth that we're trying to be able to support with the project that we're building. Jason, are you still coming through okay?
Yep, sounds good.
Okay. All right, so let me talk a little bit about the architecture of what we've come up with. And I'm showing it quick here, and then I'm going to build up to this slide again. And so essentially, this is the solution that we're working to build. And the goals are basically to be able to perform at research traffic scale to allow for network growth and improvements, and to have improved reliability and simplified support, all the while maintaining the security posture of the university. I should mention that we are using 6 different vendors by my count in terms of our solution. And remember when I said back earlier, there's a lot of challenges. You know, I said earlier, if there'd been a production solution available, we might well have just bought that. You know, some of these pieces are open source, some of them aren't. You know, some of them we can competitively bid, some of them there's only really one provider. But the long and the short of it is, you know, if you can't buy an off-the-shelf product, you spend a lot of time on people time figuring it out. And so I just want to emphasize that there's cost to having this many vendors. A huge chunk of even just doing the POC was how do you coordinate the loaning of gear from 6 different vendors simultaneously, so the terms all line up so you can get the work done and make a decision on all of it before you have to make a decision on any individual component. That was the type of challenges we were running into. The Arista piece is obviously common to many people for the tap aggregation, as is the Zeek there for traffic analysis. A lot of folks I know use Splunk. I think Humio is increasing in use, but is not nearly as much at this point. And so, there's some pieces there that we had differently. So let me go through what we did. So this is our basic, this is a third way to picture our network when we started. And here I'm only showing the 2 border routers and the networks behind them. And as you can see, we have 4 by 100 gig out. 2 of them go to Merit directly, and 2 of them go to OmniPoP, and from there to Internet 2. So the first thing we did was we put in the Corsa NSE 7200s. These were, at the time we made the decision, a pretty attractive solution. And I really think having something like this is really important to the university community. We can talk a little bit about whether or not this is, whether they're supporting this enough to make this the right thing for others going forward. But I do think this is a really great piece of hardware that's doing a lot for us. And so we can talk about that. But when we first put these in, these were basically bumping the wires. And the goal was to not interfere with traffic at all. And so we put that in place, and that's been in place ever since without any incident. Probably one of the key things we ran into early on with this piece of the infrastructure is I mentioned Alex Halderman is one of my co-PIs. When we're doing, he and others do sort of, traffic or scan the internet. And so we were very concerned about creating any perturbation in his results or his peers. And so we worked early on with Corsa to figure out how to bypass these Corsas, even if, or for how to bypass them for specific networks that were used for scanning. And so I think that's one of the first accomplishments we had in terms of one of our goals for the project was to work with the vendors and make their products better for the R&E community. And I think that's one place we had a real success there. The next thing we did is we put in place some optical taps, gigamom optical taps, which I think is a fairly conventional part of this type of architecture where the Corsas are not. It may be different now, but when we started this, the only other institution that was considering doing the Corsa route was actually Lawrence Berkeley National Labs, which kind of pioneered this approach. And so we felt like we were kind of onto something there, but the tap part is the pretty traditional part. I should mention that thanks to our information assurance group, we have something we call the mitten feed. Underneath the hood, it's CIF v2, and it sort of aggregates various threat intelligence feeds, and then we both use it internally and share it to other universities as well. And so the first thing we actually did was we started using that mitten feed to do policy enforcement via the Corsas, and the Corsas can do IPv4 at line rate at 100 gig. And so we wrote a script that allowed us to basically take the mitten data and do policy enforcement using the gigafilter on the courses themselves. And so that was the first thing that we accomplished. Then we started setting up the traditional Bro or Zeek approach here. So we have a pair of Aristas that we're doing tap aggregation and shunting. And then we probably didn't need to do both, but we wanted to compare them. We actually set up both a open source Zeek cluster and a CoreLight, a set of CoreLight devices to kind of get some experience with how each of them was running. But you notice there's no connection between Mitten and Zeek or between the Corsas and Zeek at this point in time. So we continued on, and the next piece, remember I talked about, was logs. And so the basic idea here was that traditionally our universities use Splunk. I think a lot of other universities have as well. The pricing scheme isn't, that at least we've negotiated, isn't necessarily match up well with this volume of data. It becomes pretty darn unaffordable. And so we were, instead of paying sort of by the drink, we looked for sort of a flat fee approach. And we learned about Humio from Corelight, actually, because they'd worked closely with them, and we've had a lot of success with them. And so our net costs, we got way down by taking a different approach in this case. And so we got that arrow up and running that connects the traffic analysis in Zeek to the log aggregation. But we didn't quite have that, the other two arrows from Humio over to Mitten, from Mitten back to Zeek, that didn't quite exist yet. So that's kind of what we thought we were going to do. But then we kind of kept experimenting with the architecture. And I think we kind of ended up in a different place. So where we started going was, and this part is not completely done. So I'm telling you where we're at, and we're working towards deployment over the next month or two, hopefully. And so essentially, the way we had a really great conversation with the folks at LBNL, and they've obviously been doing this for a long time, and they've got a lot of great experience here. They also are experimenting with the courses as well. And so what we kind of settled on for an architecture was that we needed a sort of a set of blocking middleware. And essentially the idea was to take data both from the Zeek output, most likely from the Corelights, that's kind of where we settled on, pass it through Humio, pass it through the blocking middleware, and use it to do policy enforcement on the courses. And then sort of supplement that data with data coming out of the Mitten threat intelligence repository. And so that's sort of the architecture that we've headed down. And now, as part of our conversation, we talked about that essentially Lawrence Berkeley Labs also has blocking middleware. They call it ACLD, which I believe has been open source for quite a while, although I don't know how widely adopted it's been. And it looks like we experimented with a little bit. I think we basically ended up going a slightly different direction. But I certainly want to give them a shout out and say that they've got a great set of software here as well. And so that's certainly an alternative to some of what we ended up doing. The other thing in there, and I'm going to talk about it a little bit more later, you notice that there are persona nodes. One of the ideas that we kind of have, and we're still working through, does it actually work like we think it will, was how do we validate that we haven't broken the science when we start changing the network security? And so the thought was to have sort of some heartbeat persona tests going, and if they start changing their behavior, then we can tie it back to what security changes that we're making at the border. Because remember, when I put on my NetBASILISK hat, the goal is not to break the science.
So I'm going to jump in really quick here, Eric, before you advance, because we did have a question. Sure. Kate Adams was curious, does Mitten mitigate or detect DDoS?
I don't think so, although I don't know if Drew's on can speak.
I just responded in the chat. It could and has, but of course it requires that the proper DDoS source threat intel exists in the feed that an organization is using for enforcement.
So for what we're doing for DDoS is actually relying on Merit's DDoS solution at this point in time. Was there anything more before I keep going, Jason?
Nope, that's good. Thank you.
Okay. So, all right. Yeah, so here's a little bit about enforcement data flows and software. So as I mentioned, we talked to Lawrence Berkeley National Labs about their ACLD implementation. What we ended up settling on was essentially a slightly different set of technologies and architecture, which we're also implementing a little bit differently with a Python-based software stack to drive the data flows. And so essentially, we're thinking through the way we're kind of thinking about it is a slow path and a fast path. And so I'm trying to figure out how the best way to say this is. In some sense, I think Chris, and who's also online, said it best early on. It's like if you put your finger on a hot stove, you want to react to it super fast. But if once you've pulled your hand away from, and it's like your lizard brain that does that reaction. It's not your thinking brain. You don't go, oh, this is hot, it's burning me, I should pull my hand away. Likewise, but if you take time and think about it, the actual right answer may be to turn off the burner. And so we sort of have the same idea of a fast path of a very low latency block of threats that are being detected in real time via Zeek on the core lights, with a goal to block threats in less than 1/10 of a second. And, but also be able to step back and say, on our slow path, what are the updates we're getting from our threat intelligence framework, that's coming from other schools that has a much slower, like 4-minute interval. And part of the reason we're doing this is we feel like there's some enforcement that we may want to do for limited periods of time. Just to give a couple of examples, obviously we're blocking on IP addresses, and so that has weaknesses. If in a shared hosting environment, we may end up blocking something that has both legitimate and illegitimate traffic, because there's multiple websites in the same environment. Likewise, just because a site seems like a threat doesn't mean we want to necessarily react the same way. There's a bunch of privately owned dorms in Ann Arbor that they're effectively dorms. They're apartment buildings that have tons and tons of students. And it may well be they have a bad actor in that apartment building, but we won't be able to tell because the provider of networking for that building has natted the whole building. And so we've got legitimate students trying to get in while we have another student who may raise the ire of our threat intelligence feeds. So there's a lot of nuance to this. And so we wanted to kind of have the ability to both have this fast path reaction and a slow path thoughtful response as well. Was there another comment? Did I see one pop up, Jason?
No, Drew just shared a URL for everybody.
Oh, great. Okay. So this is sort of the middleware blocking Arbiter code. And Chris, are you on? Do you want to take a gander at this slide?
I am, yeah. Hi, can you hear me?
Yep.
Great. This slide goes into really deep into the detail about how the fast path and slow path work together. And I won't dive into all the different arrows here, but I just wanted to talk about some of the technologies we're using here. So from the core lights, the data export that we've investigated a couple of paths there to export data from the core lights. One that's really interesting is Kafka. The core lights can be configured to stream their data to a Kafka topic, and then we could use that to write workers that would watch the topic and take actions on that. And that's a really compelling architecture to us. We're not, the main challenge there is that Kafka itself is a pretty complicated technology to run. And it's a place that we want to get to as an organization, not just in the networking team, but as an infrastructure group as a whole. But at this point, what our initial implementation plan is to use the syslog exporter because we're able to run it with more standard technologies and ones that we and our colleagues and other teams are more comfortable and familiar with. So our intention at this point is to use the syslog exporter and to send those logs, the detected threats, to a syslog ng server, and configure that to make for each event that it detects, send that to the blocking Arbiter middleware, and it can then queue up the things that it needs to do, check against, so for a given IP address, if a threat is detected from IP address X, we would queue that up to process and compare it against our whitelists, because we don't want to block networks that we are inherently trusting. Those whitelist feeds our goal there is to have those whitelist feeds come from the CIF infrastructure from Mitten, and but we want to be able to check those whitelists not just in the slow path but in the fast path also, so that if a threat does come in from a one of our networks or one of the networks that we inherently trust, we don't want to block it in this way. We might want to take it, that might require further analysis and some human intervention or slow path intervention. So we've done a proof of concept with that architecture of exporting to syslog, and then from there, syslog ng, and then from there to the Arbiter API. I'm describing a lot of steps there of syslog, and then an API, and then queuing, and then processing the queue. But even with all of those, technologies, we are targeting the 100 millisecond threshold that Eric mentioned a moment ago. And so far, it's promising. We still have more work to do there, more tuning to do, but that work is promising so far. And we've been able to put this into some dev environments and have done some work with that. The idea is that the same software stack would handle both the slow and fast paths. Currently, our slow path is implemented in a different way, but our goal is to get that into the blocking Arbiter API architecture as soon as we can. The one thing that the piece of technology that we're using here in the courses is called the gigafilter. The gigafilter is a feature of the Corsa that lets you individually or block at the granularity of individual IPv4 addresses for the entire IPv4 address space. Hence the name gigafilter for the 4.3 billion IPv4 addresses that exist in the space. Now, one of the things that works really well. It's a nice wall on the IPv4, but someone using IPv6 can just walk around the wall. And so we're also designing and thinking about ways that we can do this kind of blocking on the courses for IPv6. We can't use the gigafilter to do that because that's purely IPv4. But we've got some designs of using some other features in the courses to do the blocking for the IPv6. So that's something we're currently working on and designing and thinking about how best to implement that.
The other thing I would add, Chris, is that we're also well aware that the common design pattern is not to use the courses, but to set the ACLs on the routers. For both us and for Lawrence Berkeley National Labs, I believe the concern is the number is perhaps too high for the devices, but we are trying to design the interface here so that we could retarget it to do that as well.
Yeah, that's a really good point. So on the left side of the diagram on this slide, we've got the Corsa and the connection of both the fast and slow path there. And our architecture for the blocking Arbiter software is to make that very modular. So a Corsa would be one type of backend that it knows how to talk to. And even with our initial implementations of this, we've been very careful to factor our code so that we could drop in other backends to block against, talking to either other APIs, or that would certainly be the simplest. We're talking over this is a REST API that we're communicating with the courses and doing the management of these individual blocks and unblocks. So it would be, if another device had a REST API, that's something that we'd certainly be comfortable doing, but we'd also want to be flexible to using other methods of updating blocks on those blocking devices.
So the other thing I wanted to talk a little bit about was the logging. So essentially here, we've got two concerns. Well, maybe three. One is we need to be able to afford the logging. One is we need to be able to keep up with the volume that we're generating. And one is we need to be able to query it at a speed that allows our infrastructure assurance team, our information assurance team, to do multiple reasonable queries that might be over several months of data in a reasonable amount of time. And this is still an in-progress, in-flight discussion, but we have completed our first cycle of performance benchmark testing. We've done some software upgrades around Humio. We've kind of we've set up access to some of our storage solutions, and we think we've arrived at a recommendation to optimize how we're deploying Lumio as well. We may potentially down the line add some additional hardware, and we also still have to do some of that secondary, more than 30 days out kind of storage testing and continue the performance testing as well. And Drew spoke earlier, and John Simpkins have been doing a lot of this work as well. So there's a lot of effort in the logging space alone as well, is my key point, is that cost-wise, that's probably half the project, and or we're anticipating it to be half the project over the course of 5 years. And but also time-wise, it's a much bigger chunk maybe than I might have even originally estimated when we started this effort. All right, I know I have about 10 minutes left, so I want to segue into NetBASILISK, the research half of the project. And so this part is up and going. We start, the other part, we kind of had the proof of concept even as we were applying, whereas this part, there's a lot of new stuff here, and so we're getting this off the ground, but I think we're making some good progress. Essentially, what we're trying to do is to inform the design of scientific infrastructure and the next generation of network monitoring software. We're trying to influence the design of the next generation of switches potentially, and produce directly applicable knowledge for other research universities and network technology providers. This talk is towards that objective as well. So I mentioned our partners as well, but I'm gonna portray them in a very strange way that's only appropriate for network engineers. So very simplistically, the Atlas experiment is part of the LHC. There's a lot of data being produced off campus that we're pulling onto campus. For cryo-EM work, which I know a lot of universities are also spinning up as well, there's a lot of data on campus that we're trying to share off campus. And we picked these two sample use cases as representative of a good chunk of our scientific workflows on campus. They're certainly not completely representative, but at a crude level, they sort of reflect the two things we're trying to make sure we didn't break. Then in addition to that, we had two other things. So the first one is also sort of along the same lines. In addition to not breaking science, we didn't want to break network research. And so, Professor Halderman has ZMAP, his internet-wide measurement security measurement tool, and we didn't want to break that. And so, we looked at things like the bypass and the coursas. We're currently running, we're about to run an experiment where we're going to compare with and without that bypass if there's any impact on the performance results. And so there's a bunch of stuff to do in that space, which I also think is a really compelling science driver here as well. The other one is maybe a little bit farther afield, but they also run a project called Tap Dance, and I believe there was a conversation about this at one of the meetings over the summer in Minneapolis, in Minneapolis. There were a lot in Minneapolis. And essentially, Tap Dance is part of the effort towards refraction networking for censorship circumvention. The basic idea being that if there are nation states that are trying to censor internet access to some spaces but not others, and in particular they want to retain access to US research universities, a widely deployed refraction networking infrastructure would allow folks in affected countries to still be able to reach the internet resources as a whole, and we think we can integrate that into our NetBASILISK architecture as well. So those are some of the things that we're looking at in terms of the science drivers. And so working with our co-PIs and their various GSRAs, we're testing the reliability and performance of the NetBASILISK solution. We're looking, we're trying to quantify and qualify the impact of automated enforcement of security policy on those science and research traffic flows. We're trying to see whether or not we've actually built a highly scalable network security infrastructure like we planned. And we're also trying to use it as a way to evaluate the trade-offs between the open source and commercial versions of the Zeek network analysis framework. And giving them access to some of the Zeek data is a key piece of that, as well as the perf sonar data that we're setting up as well. So going back sort of to where I started, we're trying to develop and enforce a dynamic security policy, currently at 4x100, hopefully to scale to 16x100, or to 4x400 is the right way to say it. To have system logging that keeps up with this type of infrastructure, and to use persona infrastructure to dynamically monitor the impact of network security configuration changes. We're also trying to develop and document our privacy principles, since we are doing the port mirroring, and implement ethical privacy practices for online monitoring as well. So I'm not going to go into all the details here, but essentially we've broken out the work in this space between research, network security, the middleware pieces we talked a lot about, the monitoring and metrics, some of the community engagement endeavors we've been doing, and publishing and reporting. So a little bit more about the monitoring, and I'm going to try to wrap up, Jason, in about 3 minutes here. For the cryo-EM work, essentially what we're trying to do is we started by trying to map out what does their scientific workflow look like in terms of patterns of data movement, make sure we understand where those patterns are, see if we can figure out how to do regular latency testing and slightly less regular throughput testing in a way that doesn't impact the infrastructure, use existing persona nodes where they exist, but also put in place the ones that don't. And so we've kind of got that all outlined, and now the next steps are around setting up static test meshes and creating systems for dynamic flow simulation. Likewise with Atlas, they have an extensive, thanks to Sean and team, an extensive persona infrastructure, one of the largest in the world. And so how do we implement here what we're doing here and integrate the testing that we want to do with their existing persona infrastructure? So the work there, we've kind of identified where our target nodes are and how we're going to do this. We're in the middle of setting up the static test mesh and creating a system for dynamic flow situation. We also want to look at setting up some DTNs for simulated large data transfers, which may be some additional infrastructure. And we're also thinking that it may be useful to not just do the traditional throughput testing, but also explore using disk-to-disk testing as well through the persona framework. For the tap dance system, they've got, we're still debating sort of how the best way to handle this is, but they do generate their own statistics and their own logs. And so we're looking to see how to integrate those back into what we're doing. We're also looking at the effect of having tap dance deployed in Merit as well at University of Michigan, and see how that having it at the regional and campus level interact together as well. And then for ZMAP, the basic idea is to be able to run the same scans with and without the bypass filters that we have in place, and see if we're getting the same results. Building a second network with different IP addresses would give us quantifiably different results because people already know about the existing one, so we're working to set that up as well. Sorry, I'm going a little bit quick. And as I mentioned on the Humio piece, we've got the first cycle up and running, and we have secondary storage testing to come next. So I'm back to my original slide. Our goal is to build a world-class network available in every campus location in a manner that outpaces data-intensive research of our most talented scientists. And so we're desperately running to stay ahead of them. And we're hopeful that this approach will allow us to build a border security solution without impacting the science. And finally, we're doing a lot of research outreach. We obviously have picked 3 scientists to work with, but our goal is to figure out how to figure it out more broadly. And so we're working with our research office to figure out how do you find all the data-intensive scientists on campus? How do you reach out to them to make sure that we are working closely with them as well? And then we hope to work with the Fabric team as well as Merit Internet too on this going forward. And we've also shared at Supercomputing. Let me stop there for any questions.
All right, thank you so much, Eric. Really, really interesting stuff. We had one more come in on the group chat, and I'll certainly encourage other people to type in your questions as well. Michael Lambert wants to know, since NetBASILISK began as a research project, was there IRB involved?
Yeah, so we, all the projects that run through it have to be IRB compliant. what it really began was a production alternative network security solution. And the question is, what is the impact on the science? So we have basically, our chief privacy officer is our CISO. And so from a privacy aspect, it mostly falls under him, but the research projects themselves will always have to have appropriate IRB access for any data that they get to. Other questions?
Okay, thank you. I had one, it's a little bit of a broad question, but since you're sort of doing this both as operations and research at the same time, has there been any interesting lessons learned that you can record from one or the other yet? You know, maybe you were expecting something to happen in one way and you had a completely different outcome. Any interesting stories to relay with regards to that?
I would say there's a couple places where I think things have been more challenging, and I kind of alluded to them as we were going through, but just to kind of summarize them. I think the logging problem is bigger than I expected, and that is more of a production problem, but it's actually a research challenge to figure out how to do it right, because there just isn't an off-the-shelf solution to do this right. So that was sort of an intersection of we've been having to figure out how to do the logging right in order to do it for a production environment. So that was interesting. Likewise, you saw that our architecture from what we originally proposed around the Mitten Zeek integration, Mitten Zeek Corsa integration has evolved significantly. And so that too was an area where in order to solve a production problem, we actually kind of had to do a bunch of research and figure out how to handle this kind of problem. So both of those have been pretty interesting. I think we're just at the beginning stages in terms of the science drivers, in terms of seeing if we get an insight there or not. So I'm not sure I have an example there, but I would expect over the next 6 months we would have an answer to that question.
All right. No more questions have come in, so I'll just pause another second here and thank you again. And when you get a chance, please send me your slides. I'll make sure that those get posted, and we will have this recording available for everybody as well.
I did want to mention that, of course, all the work that we're doing that's funded by this effort will be open source. We're happy to make it available to folks, and we're happy to partner with folks. Also, I want to say thank you to the NSF for their generous support of this effort. We really appreciate the opportunity to do this work.
All right, well, thank you so much, Eric and Chris and Drew and the rest of the UMich team. Hope everybody has a good weekend. The next talk that will be occurring next week will be from Nick Braulio, who will be talking about using IPv6 as a management network protocol for the ESNet6 network. So hope everybody has a good weekend and hope to see you next week.
Thanks
Great.
again.
Thank
Appreciate
you.
it.